I welcome you to this brief introduction to sound measurement and its applications by Baseline Technologies. We will discuss why sound is important for you and how you can understand some of the basics of measurement of sound and the various applications of it. Hopefully, it will help you understand some of the fundamental concepts and lead to a more intelligent buying decision. Lastly, I would like to introduce to you our products, which are designed to solve some of the applications that we would have discussed in this presentation. Baseline Technologies offers contemporary instruments for measurement, analysis, and monitoring of vibration and sound in India. It was set up in 1990 by highly qualified and specialist engineers from IIT and continues to specialize in the above areas with no dilution in focus. It has over 3,000 users today, having supplied its instruments to almost every segment of the Indian industry, including the nuclear power sector, railways, and almost every engineering industry leader, and is considered the market leader in its segment. These instruments have achieved industry leader status over these years due to their quality, dependability, ease of use, and continued support Baseline offers all its users by way of servicing and calibration traceable to National Physical Laboratory, New Delhi. Sound is pulsations of pressure which propagate through air or any other fluid as a wave and are incident on our eardrum to cause auditory or hearing sensation. An excess of exposure to sound can harm our hearing ability and cause permanent hearing damage. It differs from vibration only in the sense of the medium that carries the oscillations. If the oscillations propagate through a solid, then it is termed vibration, and if it propagates by the movement of air or any other fluid, it is termed as sound. The measurement of sound assumes importance as the human ear has a finite response and the magnitude of the oscillations of the air pressure needs to be measured to determine its psychoacoustic effects on the human brain. Environmental noise has important public health consequences, and thus the government regulates the levels of sound permitted in different areas through the Environmental Protection Act and the Factories Act. Conformance to law requires accurate measurement of sound. The government is becoming increasingly serious about implementing the law, and violation of the EPA is considered a criminal offence in India. Manufacturers of equipment also like to specify limits to sound emitted by their products in order to be more acceptable to their customers. Sound is measured in terms of SPL or sound pressure level. Being an alternating quantity, it is essential to compute the root mean square of the oscillating pressure level. The dynamic range of the human ear is astounding, almost a ratio of 1:10 million. This is the ratio of the minimum perceivable threshold of sound to the maximum level that can be tolerated by the human ear. Due to the enormous range of these figures, a logarithmic scale is preferred, which yields easy-to-handle numbers. The measurement of sound is conventionally ratiometric and not absolute. It is 20 times the log of the ratio of pressure and a reference level which is defined as 20 micropascals. This is 0 decibel and is practically unachievable in real life. Real levels which the human ear can perceive are around 25 to 30 dB. Sound pressure level in decibels equals 20 times the log of the ratio of sound pressure to 20 micropascals. Thus, 94 dB is almost equal to 1,000,000 micropascals or 1 pascal. A 3 dB change represents a doubling of SPL. 20 dB is 10 times. The human ear responds differently to different frequencies as it has a response of approximately 20 Hz to 20,000 Hz. Thus, the effect of the same sound pressure level at very low frequencies and that at very high frequencies is considerably less than that at intermediate frequencies. The human ear follows a certain response curve with frequency. This curve has been standardized by the World Body of Audiometrists, RIAA, and the same is adopted as a standard average human ear frequency response curve. A measuring instrument is designed to weight the signals from a linear microphone type sensor according to different frequencies and convert it into an inverse form of the RIAA curve such that the output signal represents the ear response more effectively. Such a curve for moderate levels is called the A weighting curve, and the resultant readings are represented as dBA. A-weighted readings represent the response of the human ear at moderate levels and thus is the most preferred measurement parameter across the world today. For higher levels of sound, as encountered in airports, etc., the curve is slightly different and is referred to as C weighting, though this is not very often used in normal practice. While computing the root mean square of the sound waves, the applicable standards define various averaging times such as slow, fast, and impulse. Of these, slow is most often used. Slow, as defined in these standards, has a time constant of 1 second, and fast has a time constant of 125 milliseconds. There is also an impulse time constant, which is 35 milliseconds on the rising level and 1.5 seconds on the falling level. Impulse is useful for banging sounds like Diwali crackers, etc. Environmental sound, being a randomly varying quantity, needs to be averaged over a finite period of time in order to yield a single representative number of the varying quantity. If the sound has to be assessed over a long period of time extending to several minutes, hours, or a day, as in traffic noise, then the logarithmic average of the varying SPL is called LEQ. LEQ is often necessary for monitoring of environmental sounds over a period of time. SEL, which stands for Sound Exposure Level, is a figure which combines the sound level with the time period over which it is occurring. It is typically used in event-based sounds like a train pass by or an airplane flyby. SEL units are also dB, and it is the sum of LEQ in dB and 10 log T in seconds. This is best illustrated with an example. Suppose several readings of dB taken at fixed intervals were tabulated in decreasing order of magnitude. Then, ln would be the reading that is obtained after rejecting the highest n% readings of the total readings. The figure which is used often is L10 or L20. This means that we take readings over a specified period of time at specified intervals and then reject the highest 10% or 20% of the readings. The L10 value is the highest of the remaining readings. Ln is often used in assessing noise generated by projects in the vicinity of residential areas like metro rail construction, etc. Sound measurement is covered under different acts and is a legal requirement. The Environment Protection Act 1986 and rules formulated and notified in 2000 for noise pollution specify limits of dB in industrial, commercial, residential, and silent zones for night and day and require the measurement of LEQ over the period 6 a.m. to 10 p.m. as daytime and 10 p.m. to 6 a.m. as nighttime. The instruments must conform to the Indian standards, typically IS 9779-1981 and now IS 15575. These are equivalent to IEC 616721. The newer standard is slightly more liberal than the older ones in terms of the tolerances permitted. These are accuracy grades defined in the Indian and international standards covering instruments for measurement of sound. Type 1 instruments are also known as precision instruments and Type 2 as commercial instruments. In order to be legally valid, an instrument must be Type 1 accuracy and it must have a valid calibration which is traceable to standards maintained by the National Physical Laboratory in New Delhi, India. The most still of nights is typically about 25 to 30 dB, whisper is 30 dB, soft sounds such as of crickets in the night could be up to 40 dB, and a typical office would be 50 dB. A noisy party could be as much as 100 to 120 dB, and a plane taking off could be as high as 130 dB. Most firecrackers would be about 120 to 130 dB. Frequency analysis of sound is normally done within octave frequencies. The idea is to find out the frequency content of sound falling within a certain band of frequencies. Normally, this is done with steady sound levels, and the focus is selection or assessment of sound-absorbing materials or sound quality assessment. An octave is a group of frequencies, with the group of one band being double of the band before it. Finer analysis is sometimes performed in third octave frequencies, that is, in the geometric progression of frequencies, there are 3 bands in each doubling of frequency, thus making some 31 bands in the audio range. Baseline is the manufacturer of the renowned CYGNET brand of sound level meters. We offer both Type 1 and Type 2 meters, spot measurement meters, integrating LEQ meters and data loggers. Do visit our page www.baselinetechno.com to see the specifications of the various products on offer. Thank you for your time.